Okay, so we're going to walk through an example of solving a second order non-homogeneous differential equation with constant coefficients using the method of undetermined coefficients. Now, the method of undetermined coefficients basically involves making a guess, an ansatz, and then that fits the form of our solution of our homogeneous terms or non-homogeneous terms, and then figuring out what the coefficients have to be to make that work. Now, I've picked a fairly random function here, and so it does turn out that the coefficients that we end up with are a little ugly. Textbook problems usually do a slightly better job, especially in the beginning, of ensuring that your constants turn out to be reasonable. Ours are going to be a little ugly, but the method is basically the same. Okay, so we're going to start out with our function. This is our differential equations portion, and this is the forcing function term. This is our g of x, if you will. And so we're going to first solve the homogeneous function without the forcing term in order to get our base solution. And while many times this homogeneous solution doesn't have a lot of bearing on our solution, it does sometimes, and so we need to sort of keep it in mind. And we're going to need it for the solution at the end anyway. So this is our homogeneous function, and these are constant coefficient problems. And so we get our characteristic equation. And if I factor this characteristic equation, then I end up with k minus 8, and k plus 3, which gives me solutions of k equals 8 and k equals negative 3, which then go into our homogeneous portion of the differential equation, e to the 8x and e to the negative 3x. Now, if we were doing variation of parameters, we would need this to go into our formula, but all we want to look at right now is, does the homogeneous function, the solutions to the homogeneous portion, have any relationship at all to the forcing terms? If they don't, then we make a guess based on just the forcing function. If their solution here and the functions here are similar, so like we had an e to the 8x appear in the solution, then we would need to account for that by using our trick of multiplying by x. But here, e to the 8x and e to the negative 3x have nothing to do with sine x and cosine 7x, and so we're just going to proceed to our guess. Now, the thing about trig functions is that you always have to guess both sine and cosine as part of your function, because as you take derivatives, sine will become cosine and cosine will become sine. And so you need both of them to make sure things cancel out in the right way. And so we need to guess sine x and cosine x with our two unknown coefficients. But then cosine 7x is a completely different function, and so we also have to guess sine 7x and cosine 7x, because these ones will never turn into these ones or vice versa. So they're completely separate. Now, you can solve for each term separately. You can just solve for the sine 3x and just have to deal with two coefficients, and then also solve separately for the two cosine 7x and just have to deal with those two coefficients because they don't really interact. But we're going to solve them all together. And we'll see when we get down to the set of equations that, in fact, you have two equations that go together and you have two other equations that go together. Now, once we've made our guess, our ansatz, we're going to take the derivative and then the second derivative because we need to plug them back into the original differential equation. So sine becomes cosine, cosine becomes negative sine, and then here we have the chain rule. We get 7c cosine and negative 7d sine. And then when we take the derivative a second time, cosine becomes negative sine, sine becomes cosine. We get another 7 So 7 times 7 and the sign change. And then another 7 here. Now we're going to plug these derivatives into our original differential equation. So y double prime, this whole thing, gets plugged into for y double prime. And then this one, y prime, gets multiplied by -5. So this was a cosine x. This is now -5a cosine x. And negative b sine x becomes positive b sine x because multiplied by -5. 7c becomes multiplied by -5. We get -35. And then -7d times -5 becomes positive 35. And then 24, -24 times this whole thing. So -24a sine x, -24b cosine x, -24c sine 7x, and -24d cosine 7x. And that all has to equal this original equation. Now, how do we make that work? Well, what we're going to do is we're going to combine like terms, essentially. So the sine x, we've got -a sine x, and over here we've got -24a sine x, and we also have 5b sine x. So all the sine x terms on the left side of the equation, this messy side, result in -25a plus 5b, but on the other side of the equation, on the right side of the equation, there's only 3 sine x's. So we get this first expression. Same thing for cosine. So we're equating the coefficients on each side. Now, cosine, we've got -b, and -24b gives us -25b. But then we also have -5a cosine x. Those are our only cosine x terms. But on the right side of the equation, there is no cosine x term. So that becomes a 0. For the sine 7x, we've got -49. And we've got -24, which gives us the -73. And then we also have positive 35d. But there's no sine 7x's on the right side of the equation, and so that becomes a 0. And then finally, for the cosine 7x, -49 and -24 gives us -73d. And then this should be a 7. And then -35c is equal to 2 on the right side of the equation. Now, as I said before, you can see that the a's and the b's interact with each other, and the c's and the d's interact with each other. And so they're really independent of each other. And you can go ahead and you can solve these separately. And they're not that difficult to do by hand. But I also prefer just to do them in a matrix. And when you solve for these coefficients, you end up with the following. So A is -3/26, and B is 3/130 from these two equations. And then C is -35/3277, and D is -73/3277. As I said, when you pick random coefficients in random differential equations, you tend to get weird-looking answers. But 35 and 37 together are not going to give you great numbers. But we're left with these coefficients, and so we plug them into the homogeneous particular solution, the non-homogeneous particular solution, and they just get plugged in as coefficients of these initial terms. And finally, we can plug them together with the homogeneous portion to get the general solution. And again, you can verify that this is going to work in the original differential equation by plugging it into your original function. That's quite a lot of algebra, but you should be able to verify that the solution works.